clay dust sticks to sweat, and the loess wall gives a soft, gritty hiss as it sheds a thin sheet onto the trench floor. If the side slumps another few centimeters, it can shear through exposed fragments and pin people against the cut, with nowhere to step back. It is March 1974, in Lintong County outside Xi'an, when archaeologists enlarge a pit after local farmers hit fired clay shards while digging a well. Within days, the system is no longer a field. It becomes an excavation and stabilization operation. Pumps to manage groundwater, timber shoring for loess that fails in slabs, tarps to block the plateau wind, survey grids to lock every find to coordinates, and a chain of crates, padding, and trucks to move material to a lab before it dries. The stakes are concrete, paint and lacquer layers that can lift once the burial microclimate is broken, and a discovery that will redirect public money, land control, and museum infrastructure for decades. One echo line for today. This is what happens when the ground itself is fragile and the work must scale fast. A conservator faces a practical dilemma. Excavate fast enough to understand the pit plan, or slow down to consolidate pigments before they curl and drop. You can hear the compromise in the work. Trowel scraping, camera shutters, and the snap of plastic sheeting as crews build a windbreak. Hygrometers are taped to stakes. Readings decide whether a section is opened or kept damp under cover. When a gust pushes dust into the trench, workers mist the surface lightly, then cover exposed lacquer with damp cloth and plastic film to slow drying while notes and photos are taken. A near-complete warrior head appears under a brush, with faint mineral color still clinging to a lacquer base. Boots grind on grit as the team retreats from a fresh crack line along the wall. The next step is procedural. Extend the shoring, document the exposure, and hold humidity within a target range, because tomorrow the trench widens again, and each new meter increases both collapse risk and conservation loss. The wind off the way river plain carries grit that stings the eyes, and it rattles the plastic sheeting over the open trench like a loose drumskin. If wind and low humidity strip moisture too fast, pigment loss accelerates. If rain arrives, loess turns to heavy slurry and trench walls can fail without warning. Spring 1974, at the edge of the Qin Mausoleum precinct on the Loess Plateau, where the soil is fine, collapsible, and easy to cut. The geography explains both the ancient build and the modern hazard. Loess can be rammed into strong walls, which is one reason Qin builders favored packed earth construction. It is also prone to sudden slumping when water content changes. The mausoleum complex sits in a landscape of seasonal rain, cold winters, hot summers, and dust-laden winds, conditions that shape transport, drying, and long-term preservation. The engineering problem is the same across 2 millennia. Keep water away from load-bearing walls and keep air humidity stable around exposed surfaces. On site, pumps thrum and hoses spit muddy water into a ditch because even modest seepage changes wall stability. A field engineer has a practical conflict. Cut drainage quickly to protect people and exposed figures, or keep the ground undisturbed to preserve stratigraphy that records how pits were filled and roofs collapsed. Surveyors drive stakes, stretch tape, and mark a grid. Every new square opened becomes another surface that must be controlled for humidity, temperature, and dust. Loess is also a record medium. Footprints, tool marks, and construction layers can survive when protected from water flow. But once exposed, it dries and cracks, and those cracks can migrate under a row of figures. The team lays sandbags at the trench lip, sets angle braces, and restricts foot traffic near the wall because vibration can trigger a slab failure. A radio forecast mentions a cold front and a chance of rain. Tomorrow, drainage channels will be extended again, and the excavation schedule will be rewritten around the weather window and shoring capacity. Rammed earth rammers hit in a steady rhythm. Thud, thud, raising a dry haze that tastes like chalk. If compaction is uneven, a wall can crack later under roof load, and a single crack is enough for water to enter and start a slow failure. Late 3rd century BCE, at the Qin Imperial Mausoleum project near Mount Li, built during the reign of Qin Shi Huang, the first emperor who unified China in 221 BCE. The science of the site starts with scale. Ancient texts, especially Sima Qian's Records of the Grand Historian, describe vast labor mobilization for the mausoleum, sometimes given as hundreds of thousands of workers. Archaeologists treat the exact figure cautiously, but the essential point is supported by the footprint on the ground, multiple pits, workshops, and a large mound precinct laid out as an engineered complex. This is corvée labor in a legalist state. Households owe work, not just tax. The system's stress points are predictable: food, health, tools, and enforcement. A supervisor's problem is throughput. Clay must be dug, tempered, and shaped. Timber must be cut and moved. Kilns need fuel. Pits need roofs. Ramps need maintenance. Labor is organized in teams with targets because targets can be enforced. A conscripted worker has a conflict that is brutally practical: slow down to preserve strength and risk punishment, or push through exhaustion and risk injury that ends his usefulness. Control is maintained by restricted movement and penalties that are designed to deter delay, but harsh control also encourages concealment when defects appear. Qin standardization supports engineering, shared measures, repeatable forms, and limited variation where it does not slow production. But strict penalties can also suppress reporting. When defects appear, cracking earth, warped wood, a kiln batch that fires wrong, the incentive is to hide it and keep the quota moving. Archaeologists read some of that pressure in repairs, reworked pieces, and the way pits were later filled and sealed. The project expands over decades of the emperor's rule, and labor demand rises with it. The next procedural step is another round of recruitment and material requisition, because the pits cannot be completed unless workshops stay ahead of assembly. Wet clay slaps into a mold and the bench trembles as a worker presses it down with his forearms. Nearby, a kiln door radiates heat that dries sweat into salt on the skin. If moisture is trapped inside a torso when it goes into the kiln, it can crack or explode, destroying hours of labor and wasting scarce fuel. Late 3rd century BCE, in the workshop zone that fed the terracotta pits at the Qin Mausoleum near Mount Li, archaeology and material analysis point to a production method built for volume. Bodies were made in modules: legs, torsos, arms, heads, using molds and standardized dimensions, then assembled and finished by hand. You can see the logic in join lines and in the repeatability of armor plates and shoe soles. Heads show more variation, suggesting individualized finishing even when base forms were standardized. This is not just art, it is process engineering, parallel lines feeding a final assembly stage. Tools are simple but effective: wooden paddles, cords for measurement, bronze or iron scrapers for trimming, and damp cloth to control drying. Kiln technology is ceramic technology: controlled airflow, staged heating, and sufficient fuel supply. A workshop supervisor has a practical conflict: spend extra time refining surfaces for realism, or hit quotas and accept higher breakage rates. The choice affects everything downstream, because broken parts stall pit assembly. Firing and transport impose constraints on design. Hollow bodies reduce weight and firing risk, but require internal supports during shaping. Thick sections survive handling, but are harder to dry. After firing, pieces must move without impact. Straw padding and careful stacking reduce losses. When a part does fail, repair is possible, but every repair leaves a signature that later analysts can find in seams and added slip. Tomorrow's work is scheduled around the kiln cycle: load, fire, cool, then inspect for cracks. The next procedural step is to stage fuel and set drying racks, because one mistimed firing can derail an entire week of output. A whetstone grinds with a wet rasp as bronze edges are dressed, and the rinse water smells faintly metallic. If weapon parts vary outside tolerance, they won't fit shafts or trigger housings, and the assembly line stalls. If parts vanish, the loss is both material and security. Late 3rd century BCE, in the metalworking stream that supplied the Terracotta Army with real weapons. Excavations have recovered bronze swords, spears, halberds, arrowheads, and, crucially, standardized crossbow trigger mechanisms. The triggers are engineering artifacts, multiple components that must align precisely to store and release energy safely. Standardization here is visible in repeatable dimensions and interchangeable parts, the kind of production Qin also used for military equipment. Arrowheads appear in large numbers and were bundled, suggesting batch manufacture and distribution rather than one-off craft. Metalworking at this scale depends on supply: copper, tin, fuel, molds, and skilled labor. Casting produces near-shaped blanks. Finishing requires filing, grinding, and inspection. A workshop lead has a practical conflict: enforce strict rejection of flawed castings and slow output, or accept marginal parts and hope they pass in service. Theft risk adds pressure because bronze is portable value. The simplest control is guarded storage, but guarding consumes manpower that could be making parts. There is also corrosion control. Burial conditions can preserve metal surprisingly well, but exposure changes chemistry fast. In modern excavation, conservators keep surfaces stable by controlling humidity and removing salts carefully. In ancient production, oiling and careful storage reduce early corrosion, especially for sharp edges that must stay functional. Tomorrow, weapons and fittings must be allocated by pit section because the figures were placed in organized formations with specific armaments. The next procedural step is a fit check of trigger sets and a recount of arrow bundles before they move to the assembly ramps. Under the lights, a thin skin of lacquer curls and makes a faint crackling sound, like dry leaves, while pigment grains dust the glove when a finger brushes too close. If that lacquer detaches, the color goes with it, and the figure's surface record is lost in minutes. Late 20th and early 21st century conservation work at the Terracotta Army site near Xi'an has had to treat excavation itself as a destructive process unless climate and chemistry are controlled. Scientific analysis shows the warriors were originally painted. A lacquer layer acted as a binder and base. Mineral pigments added color, and some details were shaded and patterned. The problem is mismatch. Lacquer that stayed stable underground can shrink and separate when exposed to lower humidity and changing temperature. That is why early excavations saw colors flake rapidly after opening. Conservation has responded with controlled environments, rapid stabilization, and careful removal of soluble salts that accelerate deterioration. This is engineering of preservation: tents and halls to buffer climate, sealed storage for fragments, and workflows that synchronize excavation speed with lab capacity. A conservator's inner conflict is practical: keep the site open and the research moving, or slow the excavation to a crawl so surfaces can be stabilized to a higher standard. The choice affects funding and public access, but it also affects what data survives for future methods that do not exist yet. The pigments themselves carry supply information from the Qin period. Mineral sources, processing methods, and application techniques point to organized procurement and trained specialists. Even brushstroke direction can indicate the order of painting relative to assembly. In modern labs, microscopes and spectroscopy turn those traces into measurable datasets, but only if the surfaces survive long enough to be sampled. Next, a new section of pit will be opened under tighter humidity control, and the team will test stabilization protocols on a small exposure first. The procedure is cautious by design, because every improvement is judged by one metric: how much color stays on the clay after a month. Wood beams creak under load, and reed matting gives off a damp, grassy smell when it's laid over fresh earth. If the roof system sags, the weight of the cover layer drives beams down into the ranks, snapping clay and crushing what has already been assembled. Late 3rd century BCE, in the construction of the terracotta pits, large underground halls built to hold formations of soldiers, horses, and chariots near the emperor's tomb mound. Archaeology shows the pits were engineered spaces, not simple holes. Floors were leveled and, in places, fitted with drainage features to manage seepage. Side walls and internal partitions created bays that stabilized the roof span and organized assembly. Over the figures, builders laid heavy timber beams, then reed mats, then layers of packed earth, creating a concealed underground hall that could support a thick cover. This roof design is a logistics problem. Timber must be cut, transported, and set accurately. Spans must balance structural safety against material cost and time. An engineering lead has a practical conflict: specify heavier beams and more partitions for stability, or accept thinner members to save timber and speed completion. The choice affects failure probability, and failure has two forms: collapse during construction, or collapse later as moisture and time weaken supports. The layout inside the pits is also functional. Formations align with Qin military organization, front ranks, supporting units, and command elements, each with different equipment. That means assembly must coordinate bodies, heads, weapons, and placement, like staging a warehouse pick list under tight spatial constraints. Once covered, maintenance access is essentially gone. Drainage and roof performance have to be right the first time. Evidence from the site indicates that at least some pits suffered burning and destruction, with collapsed roofs and broken figures. That destruction becomes another engineering layer to interpret, separating original design from later damage. Next, archaeologists will map collapse zones in detail, because the pattern of broken beams and scorched earth can help reconstruct what happened after the Qin state fell. Mud sucks at cart wheels and the oxen breathe in loud, wet bursts, while charcoal dust smears hands black as loads are adjusted under a cold drizzle. If fuel arrives damp or late, kiln temperatures drop and batches fail. If timber is delayed, roofs and shoring wait, and idle labor still consumes food. Late 3rd century BCE, on the supply corridors linking the Mountly precinct to quarries, clay banks, forests, and the Wei River transport network. A project the size of the terracotta pits is a materials equation. Clay must be abundant and workable. Water must be available for tempering and for human consumption. Fuel must be continuous for kills. Timber must come in lengths that match roof design. Seasonality matters. Floods shift river channels and soak fuel. Winter cold slows transport and changes drying behavior. Dust storms increase surface abrasion and drying stress on unfired clay. The Qin state had infrastructure advantages, roads, standardized measures, and organized labor, but that does not eliminate bottlenecks. A transport supervisor has a practical conflict. Push convoys hard to meet deadlines and accept higher breakage and animal loss, or slow down to reduce waste and risk punishment for delay. Every choice moves cost between categories: fuel, labor time, replacement parts, and food. The archaeological record preserves hints of this logistics web. Kiln areas, workshops, and debris fields indicate where production clustered. Tool marks and standardized components indicate repeatable processes that depend on steady resupply. Even the distribution of broken fragments can reflect transport damage versus on-site failure. None of that is accidental. It is the residue of scheduling decisions made under pressure. When a supply line fails, the system does not stop cleanly. It frays, repairs are improvised, lower quality inputs are substituted, and defects rise. That is when enforcement tightens, because the state reads material loss as loss of control. Next, the calendar turns toward the wet season, and planners must decide which work phases can tolerate delay and which, like firing, cannot be paused without compounding waste. Charred earth smells bitter when it's dampened for excavation, and blackened beam fragments crumble to powder between gloved fingers. If you misread this layer, you misattribute damage. A collapsed roof from design failure looks different from a roof driven down by fire and deliberate destruction. Early 2nd century BCE, after the Qin dynasty collapses and the mausoleum precinct becomes a target in a landscape of war and factional control. Historical tradition holds that forces associated with Xi'an entered the mausoleum area, looted, and burned structures. Archaeology at the terracotta pits supports destruction, burned layers, collapsed roofs, shattered figures, and signs that weapons were removed from some hands. The system under stress has changed. It is no longer a controlled construction project, but a contested resource site. Bronze weapons are immediate value for armies. Timber and stored materials are fuel and shelter. Symbols of Qin authority become targets because political legitimacy is being renegotiated by force. A commander in a raiding force has a practical conflict. Spend time extracting usable weapons and risk ambush, or torch the site quickly to deny it to rivals and to strike at Qin legitimacy. Fire solves one problem and creates another. Heat weakens timber, roofs collapse, and the falling mass breaks terracotta in patterns that archaeologists can map. Once the roof is down, loess and ash seal the damage, creating a time capsule of violence. This matters for engineering interpretation. When you see broken limbs and scattered heads, you need to know whether they failed during production, during assembly, or during destruction. Burn temperature, charcoal distribution, and beam orientation become data. Modern excavation uses that data to reconstruct sequence, fire, collapse, looting, then burial by later fill and erosion. Next, the investigation tightens to specific base sections where burn intensity differs. The team will sample ash and char layers and document beamfall directions, because those measurements are how you separate accident from attack. A drill core comes up cold and damp, smelling of earth and minerals, while the lab instrument clicks through a measurement cycle. If you open the central tomb without the right controls, you may destroy organic materials, painted surfaces, and microclimates that have survived for more than 2,000 years. If you never open it, key questions remain locked behind a mound. Today's Xi'an outskirts, at the central burial mound of Qin Shi Huang, still largely unexcavated. This secret tomb, in popular retellings, has a technical backbone. Sima Qian describes a subterranean palace with elaborate contents, defensive mechanisms, and rivers of mercury. Archaeologists treat the text critically, but modern surveys have reported elevated mercury concentrations in soil near the mound, which is consistent with, though not definitive proof of, mercury use. The engineering intent would be clear: create a sealed environment, deter intrusion, and maintain a controlled internal space. Sealing is not just piling dirt. It involves layered compaction, water management, and protection against tunneling. In the Qin period, the same packed earth technology used in walls could produce dense, low permeability barriers. The failure modes are familiar: cracks from settlement, water infiltration, and later human disturbance. An excavation director faces a practical conflict: the scientific value of opening the chamber versus the risk of irreversible loss if conservation methods are not ready for what is inside. Modern archaeology treats the mound as an active system with constraints: legal protection, public expectation, and technical limits. Non-invasive methods, geophysics, remote sensing, soil chemistry, offer partial answers while buying time for better conservation. But partial answers also generate pressure, because funding and attention favor dramatic access. Next, survey teams plan a new round of geophysical mapping around the mound perimeter and drainage lines. The procedural goal is simple: reduce uncertainty about structure and hazards before anyone makes the irreversible decision to cut a shaft. Inside the main hall, the HVAC vents hum and the air feels cooler and drier than outside, while thousands of footsteps create a constant low vibration across the concrete walkways. If humidity swings, pigments and lacquer remain at risk. If crowds concentrate in one area, CO2, heat, and accidental contact increase damage probability. Modern day at the Terracotta Army Museum complex near Xi'an, built to keep excavation visible while protecting what has been exposed. This is infrastructure under continuous load. The pits function like open laboratories inside public buildings. Climate control is not comfort, it is conservation. Lighting must be bright enough for visitors, but limited to reduce heating and photochemical stress. Barriers must prevent touching without blocking sight lines. Drainage and foundations must handle local rainfall and groundwater, because moisture migration is the enemy of both lush stability and artifact surfaces. A site manager has a practical conflict: maximize visitor access that funds the operation, or restrict flow in close sections to stabilize conditions. Every decision shows up in maintenance work: filter changes, dehumidifier service, vibration monitoring, and emergency responses to leaks. Conservation staff work in small windows before opening hours, using brushes, micro tools, and controlled suction that sounds like a quiet whine in the empty hall. Public order is part of the system. Crowd control, signage, security patrols, and surveillance reduce theft and accidental damage. The economics are equally direct. Ticket revenue supports staffing, labs, and ongoing excavation, but it also creates pressure to keep the most famous pits open even when conditions argue for closure. Next, the calendar moves toward a holiday surge when visitor numbers spike. The procedural question is whether to limit entry and protect microclimates, or absorb the load and accept higher conservation risk in exchange for revenue and political expectations. A laser scanner ticks across a warrior's face with a faint mechanical chirp, and the surface texture appears on a monitor as a dense cloud of points. If documentation is incomplete, later conservation or reconstruction becomes guesswork. If you overhandle the object to capture perfect data, you increase physical risk. Modern research at the Terracotta Army site uses measurement to replace speculation wherever possible. Archaeologists study manufacturing through repeatable traces, join seams between modules, tool marks, clay composition, firing behavior, and patterns in how parts fit. Digital recording, photogrammetry, 3D scanning, and mapped condition surveys lets teams compare thousands of fragments without moving them repeatedly. Material analysis identifies pigments, lacquer layers, and corrosion products, tying surface preservation to burial microclimate and modern display conditions. There is also evidence embedded in metal. Some bronze weapons bear inscriptions that record production information, and standardized crossbow triggers show interchangeability. That is quality control expressed as engineering. Make parts that fit regardless of which team made them. A researcher's inner conflict is practical. Publish quickly to secure funding and career stability, or spend years building a dataset robust enough to survive critique. The trade-off is time versus confidence. Repair work becomes a parallel system. Broken figures are reassembled with modern supports, adhesives, and internal mounts, but every intervention must be documented so future teams can reverse it. A fragment's weight, fracture surface, and fit angle are recorded because reconstruction is an optimization problem, not a guess. The sound in the lab is quiet. Brushes, calipers clicking, printers spitting labels for storage trays. Next, the team plans a new full-pit digital survey to link every figure to exact coordinates and condition states. The procedural goal is to predict where deterioration will accelerate, so interventions can be scheduled before loss occurs. A security radio crackles at the fence line, and beyond the protected zone you can hear the flat metallic clang of modern construction in the distance. If development cuts into the buffer area, you risk damaging unexcavated features, workshops, drains, roads, before they are even mapped. If protection is too strict, local communities lose land use and income, and pressure builds in predictable ways. Modern Xi'an's expansion reaches the same landscape that holds the mausoleum precinct. Heritage management is a system of law, planning, and enforcement. The mausoleum of the first Qin emperor and its terracotta pits are recognized internationally, and protection includes mapped boundaries, controlled excavation permits, and restrictions on building and soil removal. These rules exist because archaeology is not just about what is visible. Subsurface features carry evidence for supply chains, labor organization, and engineering choices. A local administrator faces a practical conflict: approve infrastructure and housing that generate jobs and revenue, or delay projects to protect archaeological potential that is valuable but not immediately visible. Compensation, resettlement, and land use negotiations become part of preservation because people live next to the site and their incentives matter. Illegal digging is the other pressure point. High-value artifacts create incentives for looting, and looting tends to target the easiest-to-reach areas first, which can be exactly where undocumented features survive. The response is operational. Patrols and surveillance reduce opportunistic theft, permitting controls limit large-scale soil disturbance. Before major groundworks, teams run field walking, test pits, and geophysical surveys, then decide whether salvage excavation is needed. It is a triage model. Protect the highest value zones, document what cannot be protected, and keep a clear chain of accountability when contractors move in. Next, a new road alignment proposal will trigger a buffer zone review and a rapid survey campaign. The procedural task is to test before digging, because once machines cut into loess, the record is gone. A core sample is split with a clean snap, and the exposed soil face shows faint bands, compaction layers you can feel with a fingertip as ridges and smooth planes. If the site is treated as a finished tourist attraction, research slows and unknown zones remain vulnerable. If it is treated as a constantly open dig, preservation risks climb with every new exposure. Modern management of the Terracotta Army is a long-term balance between access, science, and conservation capacity. The measurable legacy of the terracotta system is not just the headline number of figures, often cited as around 8,000 soldiers plus horses and chariots in the main pits, but the evidence for organized, modular production. standardized components, interchangeable weapon parts, and workshop clustering show process control. The pits themselves show civil engineering, partition bays, roof and cover systems, and drainage thinking adapted to lush terrain. These are the same constraints that shape large projects today: material flow, quality control, and failure management. Institutionally, the site forces policy decisions. Protection zones restrict development. Museums and labs require budgets and trained staff. Conservation science has to evolve as new materials are exposed, and that research is expensive. A decision-maker's inner conflict is practical. Invest in slow, careful science that protects future value, or prioritize visible progress. New halls, new excavations, bigger visitor numbers. That pays back quickly in revenue and political credit. The Qin tomb mound remains largely unopened, which keeps the biggest unknown intact: what survives inside and in what condition. Non-invasive survey reduces risk, but it also means conclusions are incremental and sometimes contested. The system's resilience is shown in how much has survived. Its fragility is shown in how fast surfaces can fail after exposure. Next, the site enters another funding cycle that will determine staffing levels, lab throughput, and how many square meters can be opened safely. The procedural question is not, can we dig, but can we stabilize what we uncover before the next section is exposed? In the conservation lab, a small suction unit hums softly while a brush lifts dust from a crack line no wider than a hair. If that crack propagates, a flake of lacquer can detach, and a pattern of paint, data about materials, procurement, and technique disappears. Present day, at the Terracotta Army conservation facilities serving the excavation halls near Xi'an. After decades of modern work on the pits, the picture is sharper and also more cautious. We can map formations and construction phases. We can identify modular manufacture and standardized weapon engineering. We can measure pigments, lacquers, clays, and corrosion processes. We can document destruction layers that fit a period of post-Qin conflict. And we can state, with evidence, what remains unknown. Large areas are still buried, and the central tomb has not been opened because conservation risks remain high and internal conditions are still uncertain. A senior conservator's inner conflict is practical. Every successful stabilization invites another excavation request, and every new excavation increases the workload and the long-term liability. Staff capacity, climate control, and storage space are limiting resources, not curiosity. Training is also a bottleneck. It takes years to build technicians who can lift painted clay safely, and a single rush season can undo that investment in one afternoon of surface loss. Public order and economics never disappear. Visitor flow funds the site and also adds vibration, heat, and accidental contact risk. Security has to deter theft and protect fragile areas, especially when new exposures make the site feel fresh to the public. Outside the halls, the Lush Plateau wind keeps blowing, and groundwater keeps moving, and both have to be managed whether or not anyone digs. The Terracotta Army is a discovery that never becomes fully finished because preservation is maintenance. Next, a small test area will be opened under controlled humidity, documented in high resolution, and then paused for condition monitoring. The procedure is deliberate. Measure first, intervene second, and only then decide how much more ground can be safely removed.